In this video, we're going to look at another method of generating Gaussian distributed or normally distributed random variates. In a previous video, we looked at how to do this using the central limit theorem. So on the left-hand side, I've got the script that we wrote before. We'll just check that it's running. There we are. It produces a Gaussian variate, a set of Gaussian distributed random variates. So that was done using a central limit theorem where I took several numbers, in this case 12 numbers, and I added them together. And it made use of the central limit theorem to provide a Gaussian variate which was approximately normally distributed. Now this transformation method, this so-called Box-Muller transform, is a geometrical method. This is the Wikipedia page for that, and I'm going to scroll down. You can look in a bit more detail about why it is that the sampling procedure we're going to use produces a Gaussian distributed variate. You can see there's a picture of this on the Wikipedia page. I'm just going to go straight ahead and implement this method. So you can see that I can generate with two uniform variates, U1 and U2, I can generate a Gaussian variate, Z0, and I can generate another Gaussian variate, Z1. So I'm actually going to dispense with the second one. I'm just going to use two uniform variates to generate a single Gaussian variate, but I'm going to note that it's possible to generate two Gaussian variates from the same pair of uniform variates. I'm obviously not going to do that. So how do I do that? Well, let's say I want to generate some samples. I'm going to get rid of the previous code. Just to begin with, generate 100 samples. And so each sample, I simply enter the formula here. I'll take the square root of -2 times log, is it log or ln, depending on the programming language. We'll check that in a second. So we'll do log of a random number from 0 to 1, and we'll take the square root of that and multiply it by the cos of 2 times pi times the other random variate. And by writing it in this form, I don't need to store the random variates in variables, which I would need to do if I wanted to generate two Gaussian variates from the same pair of uniform variates. I'm just not going to bother to do that. So let's just check help log, check I'm using the right function. Yes, we are. So this should give us Gaussian variate. So if I just copy this expression, I can type that in at the command line to check that it's working, and I run it. And it looks like it's producing something which looks about right. I can run it 100 times and then histogram that. It's kind of looking okay. And let's run it 1,000 times. Save the script again and run it again. And it's beginning to look okay. Let's run it 10,000 times. So it's running fairly quickly, even with 10,000 variates. And there we have it. So this has, these Gaussian variates have 0 mean and unit standard deviation. Now it's interesting to compare and contrast this method, the Box-Muller method, of generating random numbers, which are Gaussian distributed, compared to the previous central limit theorem method. In the previous method, we added together 12 uniform random numbers, 12 uniform variates, or perhaps a smaller or greater number, but 12 is relatively convenient. And the result of adding those 12 numbers together and then subtracting 6 was to give us a Gaussian distributed random variate approximately with unit variance and standard deviation. Now that procedure, generating 12 random numbers and then adding them together, is quite efficient. The only deficiency of the method is it doesn't allow us to generate numbers which are very far away from the mean. The difference of the Box-Muller method is we only have to generate two random numbers, here and here, but then we have a fairly involved mathematical procedure to convert those two random numbers into our Gaussian variate. You can see that we're having to multiply by pi here, multiply by 2, then take the cosine. We need to do a logarithm of this random number and then square root it, then multiply all the values together. So there's a lot of mathematical operations which have to be performed for each and every one of these variates in order to generate a single Gaussian variate. So that's rather inefficient. The advantage of it, of course, is that in principle I can generate any number I like. I can generate numbers which are many sigmas away from the mean, which of course is advantageous in many situations. Now, that comparison is an example of the kind of things you need to watch out for with random number generation. You can see we have this basic form for the uniform for the Gaussian variates, as we can see here, and one way of improving the efficiency would be to use the second calculation as well as the first calculation. There are other methods, and I'll just scroll down and I'll leave it to the viewer to implement these other methods. There is a so-called polar form, which we see down here, and there are other forms, including the polar method and even more complex methods, which are there to improve the efficiency with which I can generate the variates. So in a nutshell, we need to worry about the efficiency of the method and also its validity. So the Box-Muller method is fairly inefficient. It uses a complex series of evaluations in order to obtain the random variate. But it is valid. It can generate, at least as well as these numbers inside are uniform. The Gaussian variate it generates can give rise to variates which are well away from the mean. The central limit method that we saw in the previous video is more efficient but less valid. However, that validity may be good enough for the situation that we find ourselves in, so it depends on the application. In the following video, we'll show yet another method for generating Gaussian variates.